X-array, we did some more statistical analysis, and we also were interested in getting down files from Google Drive without downloading them locally. So these were kind of the roughly 4 tasks we tried to tackle in individual groups. And for the overview of the data, I will give over to Hushna.
So we had digital elevation or DEM TIFF files from 2003 to 2016, and we wanted to get a trend analysis and do statistical computation on the per pixel things so that we know how things are changing over pixels. So we basically used 2 approaches. One was the normal NumPy arrays approach, and one was we got the data ingested into X arrays and tried to play with it. And then one of our group devised a way to download data from Google Drive without logging in and clipping it on each of the files. They just can call the files from Google Drive and do manipulations on them. So I'll hand over the mic to Howard, who did the statistical computation using NumPy arrays.
Okay, thanks. So we had 29 data files representing different times. And they are plotted below here. We used GDAL and PyGeo tools to read them in based on the Rainier dem example file from David. And also we used X-array to accomplish the same, to read the data in. So with X-array, we discovered that it was really easy to do statistical plots of the data sets. So here you see, so basically all the timestamps had a different cover of the region. So to get a mean elevation, we accomplished that with 1 line of code with X-arrays. And also this greenish yellow figure here shows the overlap of the data sets. So yellow means that the pixel is covered by many datasets, while dark means bad coverage. Further, we experimented with masking. So we are looking at one glacier and not the entire region. So here we used PyGeo tools and GeoLib within PyGeo tools to read shapefiles to get the masks, and we used GeoPandas to filter out all masks except for the Khumbu Glacier mask, so that we only got the data we were interested in. Based on David's example code, we did a comparison of the altitude, but this doesn't give that much meaningful information directly. So Lynn did something smarter to analyze the data.
So basically what we want is to know how much does the glacier change per year, so in meters per year. And we had this time series of the elevation for every pixel. So what we did is just a linear regression to find the slope of change. And we plotted this here. And we see that it ranges, so the maximum is I think almost 20 meters per year in increase, and we have like around minus 10 meters in decrease. But we cannot see much structure here, so this is a zoom in, so basically we changed the scale so you can see a little bit better the structure, what's happening. And what's red are those zones where we had a decrease over the time, and what's in blue, like more on the right side, is where we had mostly an increase or decrease. I mean, you can see that's like blue and red scattered. So this plot doesn't even include our oldest observation from 2003. So this is just 2012 to 2016. And despite our fluctuations between summer and winter, we can see that there is a clear trend. So what's happening basically is that in the higher elevations, which are on the right, the situation kind of stayed the same. I mean, of course, you have changes. So some locations gained some snow, some lost some snow, like there are cracks and ice falls. But on the on the tail of the glacier, we see this decrease. So there's the glacier is actually melting. And to confirm this, we also plotted a histogram. So the x-axis here is the elevation, and we plotted the histogram of the change rate in meters per year. So what we basically see is that on the right, the higher elevation areas are kind of scattered around 0. So of course things are happening on the individual pixel level, but overall the glacier kind of stays the same. But on the left side, on the lower elevation areas, we do see clearly here that we have a decrease in the elevation. Who's next? Okay. Change. Excellent. Sorry, I need to get out of there and then do that.
How do we get
I don't
back?
either. Where's the escape button?
Actually, go to the end viewer there. Escape. Where's the escape button?
I don't know.
You have to go back. There.
Okay, so use these links down here, because this one,
Yeah, that,
Oh, you're gonna Joe's?
is it,
That's already been covered. So
Oh, okay.
this one, right?
So for the second part of the glacier analysis, my name's Michelle. Hi, everyone. We wanted to look into using some interactive visualization tools. So this is going to be a really brief dip your toe in sort of thing, and that I'm sure some other groups will just jump right into the pool with later on. So just a sneak preview right now. The different libraries that we used for this was Bokeh. It's a plotting library that emphasizes interactive visualization, and it basically runs JavaScript but is controlled by Python. We also played around with IPy widgets, HoloViews, and also relied on Matplotlib and Plotly. So for the very first graph, we wanted to graph the distance along a transect that a user could draw along the glacier, and then determine from that transect that was user input what the elevation change was at certain points along that transect. So using Bokeh, they have a lot of in-box tools that you can generate. For someone who knows very little about this sort of thing, I created this pretty quickly, and it looks very nice, if I do say so myself. You can pan around, you can reset it, you can output HTML files or image files and just save directly from this interface. So that was pretty cool. And then for the HoloViews, it gets a little bit fancier. We decided to use kind of the same layout where you have distance along the transect on the x-axis, and then the annual elevation change that was along that transect on the y-axis. And then you could flip through essentially those different images, so from 2003, 2012 to 2016, and visualize it that way. This, I want to emphasize, is not real data. I just made this up so it would work well for this presentation, but you could use real data. Yeah, that's all.
So, our final piece will focus on velocity mapping.
Use the bottom. That one's not ready yet.
Oh, okay. Yeah, so final piece focused on is what I was working on, which just confused a little bit. But yeah, so I was doing a Google Drive integration with how we were loading some of the data sets. So the main thing for Google Drive implementation was I found this library called PyDrive that was necessary to use. Because in order to use Google's API service, it requires a lot of intricacies that I'm not going to do from scratch, but it's always good to copy code from others. So there's an established drive from a library that you can import from into Conda, or whatever environment you're working in. When we do so, you can basically you have to authenticate with Google Drive. So basically, if I were to run this code here, basically it automatically pops up in a login window for your own Google account, and it just gives you authentication to be able to access other things. What we want to do at the end was actually make that anonymous, just so it could access a Google Drive without that authentication piece. but that was not possible, at least with how Google's API is implemented. So, but this one works really well. Actually, just you run the code, out pops the box, and you just go back in, and so it worked rather smoothly at the end. But anyway, once you then have that authenticated, you just need the link to your folder that you have on Google Drive, and then you can run this command to get basically the metadata of all the folders, files in that folder. Then you can look for the files you need. So in this case, you wanted these specific folder, files, the ones with 32-meter resolution that are transformed into TIFF files. And that then we can list them out. You can see all the files we got with the actual file names plus their unique file IDs. So you can then use those unique file IDs and say GDAL to construct links to them. Or you can just take actually from these metadata files at a direct web content link. So when we do that, you can then just take gdal.openurl, and you can see we have information of the file that we this from the internet, and you can plot it. So then you can start doing what you need to do with the data. So down the line, if we had more time, we would implement these all together in terms of the workflow from the previous projects we showed you. But this shows like a usability scenario case where you can actively interact with, say, your Google Drive files without necessarily always having to download into your working directory and use up space in your computer. You just would only download the files you need, and that is handled in the cloud as opposed to always on your local working station. So we thank you for your time and listening to us, and we're happy to field.
We got one more?
One more thing? Yeah.
Just last second.
Or we have one more thing.
Don't go home yet.
But wait, there's more. And let me just pull it up. I think we can get to it like this.
Okay.
Yep.
Okay, here's the velocity mapping section. It's still the Kunbu Glacier. From the literature, it's been shown to have the velocity change in this area, and this is a figure from 1992 to 2002, and my goal is trying to see if I can plot a figure with the new data, and we are using Python tools called VMap developed by David Shin, and here's the link to the repo. It was built based on a tool developed by NASA, ASP package. Here's a figure show the data and the workflow. I'm using the 8-meter resolution DEM time series for this region. It's in a GOT format. What this package does is it takes image from at 2 different times. Then the first step is to use this Python script called VMap to generate the dispersity. And the second one will convert the dispersity to the velocity. And the final product will be the mean velocity during this time period. Unfortunately, I'm running out of space on the Jupyter Hub because I have like only 0 gigabytes left on the cloud, so it won't allow me to either upload data or deleting data, so I don't have my figure here yet, but hopefully we can fix this later. Yeah, that's it.
We'll gladly field any questions.
For Stalin.
Oh, great. Okay, hi guys. We're #snowmelt, and our project was to basically look at this specific region in California and try to see topographical influences on snowmelt and in a quote-unquote warming world. So I'll explain that in a minute. So we were using ASO data, which is Airborne Snow Observatory LiDAR data. And our location is the Tuolumne River Basin, and that's in California, and you can see that in this cute little map here. And so this river basin was of interest because it is a major water supply for California. And the winter snowpack that builds up in that area is naturally forming water supply, and so we're interested in seeing how that's going to be affected if our temperatures continue to increase throughout the winter season. So our data. So like I said, we're using the ASO LiDAR data, and this provides the snapshots of snow depth throughout the snowmelt season. And so our snowmelt season is defined by, I think it was March, April, May-ish. February. Was it that? Oh, okay, yeah, so February too. And so this was the snow depth, and it was at 30-meter resolution is what we ended up using just because we don't have much time and wanted to have it be quick. And then we also had the DEM for that area of the watershed, and that was at 30-meter resolution also. And there's a link to the data there. And this plot is just to show you the watershed itself. So the original map was like zoomed out, and now this is the actual watershed, and that's the DEM of that watershed. So our group, so we had like questions and goals for our group. So our science questions were mostly, like I said, we wanted to see that change in snow depth being affected by warmer temperatures. And so we were kind of using 2015 as that warmer year because it was compared to averages a lot warmer. So we were using 2014, 2016 as a normal year, and then 2015 as a warmer year. And we were interested in topographical influences like slope, aspect, elevation on this watershed, and comparing that to the snow depths and how all these things are interconnected. Yeah, so I already said that. All right, so then group goals. So we're kind of newer to a lot of the stuff that were introduced during Geohackweek. So a major part of our group goals were just get familiar with Jupyter Notebooks, be really good at using them, get familiar with GitHub, be really good in a collaborative environment, and then raster manipulation, because a lot of us hadn't done that before, and then Python statistics. So I think we did a great job as a group working on our group goals for sure. Okay, I'm gonna pass it off. Who's next?
It kind of goes back. I don't know what that plot is. I did the next one, the Seaborn one, but I can talk about.
Oh, this one. I think. Oh, loading the data. Do you want to talk about that? Okay, and then I think.
So we had 3 different years worth of data in TIFF files, and so I just wrote some Python code here to look through the folder where all the data was being stored, and then load every raster file into a NumPy array, sort of in a dict by year, and it made it a lot easier to work with it all within our program there. And
then we just wanted to kind of dive into the data, familiarize ourselves with it a little bit. So we made these histograms in Seaborn, which just shows you each one of those histograms is different. So the first one's going from February of 2015 to March of 2015, and it's just the frequency of the change in snow depth. So you'll see the ones that are, those first few changes, those are showing an increase in snow depth, whereas towards the end of the season we see that the change in snow depth becomes mostly negative, and so that's where we're seeing a lot of the snow melting and melt rates increasing. And so
also with that loaded data, just you're plotting some basin-wide means, the blue line, just the mean snow depth across the entire basin, and the dotted lines, the mean difference. And each data point along the timeline is a single ASO flight, or the instance of the differences, it's the delta between 2 consecutive flights. And that's just showing comparison of snow depths and deltas in 2014 there on the top, versus 2015 where snowpack was much lower.
Part of our group goal was to learn about using all the different scientific libraries that were introduced to us this week. And so just to visualize all our data across each season, I was able to plot essentially just the data by each year. And I did this first before the X-ray tutorial, just with NumPy and Matplotlib, and it was at least 3 times as much code. And then we learned about X-ray, and I was able to make this entire large plot for all 3 years, just with those few lines of code above. And then we wanted to look a little bit at the sort of rate of snow depth change. And so we didn't dive into this for every year, but actually we did. Sorry. So I did some manipulation on the data to make sure that we were only looking at snow loss, because over the course of our season, there were some data points where we had snow accumulation because of large storms in late spring and stuff. So we looked at snow loss, and then all our data points were from different sort of intervals throughout the snowmelt season, and so we had to normalize the rate or the time between each data point. So we just plotted the sort of snow loss per day at every point over the course of each season, the mean snow loss per day. And then to try to help visualize that a little bit, I plotted it on top of an aspect map, so it's not super informative, but if you look closely, you can see, as expected, that like the south aspects have a lot faster rates of snowmelt.
And then to take a look at the influence of elevation on the snow depth change, we first needed to look at like the distribution of the elevations. And so this is a pretty high elevation watershed. As you can see, the majority of it is in the 3,000 meter range, I guess that is. And so after seeing that and thinking about how we could analyze snow depth change over elevations, we decided that we needed to divide it into elevation bands so that we wouldn't be analyzing over continuous data, but instead looking at it in divided bins. And so what we did here, which I guess I'm not showing the code for, is we divided the DEM into elevation bands of 300 meters, I believe. And then here we plotted the difference in snow depth just between the first 2 of our flights in 2014. So this difference in snow depth between February and March 2014 at these different elevations in our watershed. And so, left to right, top to bottom, we're in our lowest elevation, actually has accumulation, and then as you go into the higher elevations, you can see that we have more significant accumulation in that early season. Presumably, if we kept plotting this later into the season, we would see those numbers go down, and it will be interesting to see in the future whether snowmelt is higher later in the season at higher elevations, lower elevations, things of that nature.
Since we were looking at what this snow melt in the warmer years, so I wanted to quantify how warm was the year 2015. So I grabbed temperature and precipitation data. So for temperature, I grabbed mean, minimum, and maximum temperature from PRISM observation. And now this data was for entire US, so I used a bunch of libraries we learned this week to reproject and clip the data to watershed, and then I did some basic differences. As in this plot, the top panel has 2015 minus 2014 temperatures, and the bottom has 2015 minus 2016, and then it's T mean, max, and mean. As you can see, 2015 was quite warmer as compared to both the years. And then I did similar analysis with precipitation, and 2015 was actually drier, a lot drier as compared to 2016, somewhat drier as compared to 2014 over some region of the watershed. That's all we have.
Yeah, that's it. Is there any questions?
Questions?
Yeah.
So 2015 was a really dry, really warm year, but mostly really dry. I was wondering why you chose 2014 and 2016 as comparison years when 2014, I believe, was also a pretty low snow year.
Those are the years we were given data.
But 2016 was a significantly higher precipitation, even compared to the drought. Just like on a norm, it was significantly higher. But yeah, the data is the answer. Yeah.
Anyone else?
Oh, I got one question.
Did I just hear?
Just curious how your experience was using X-array or whoever used that. Was it easy to learn, hard to learn? I'm just trying to compare for my...
It was helpful to have the tutorial code to go through, but at the same time, I still didn't fully understand all the different arguments that you had to give to X-array. And well, I found the Python documentation for X-array was helpful as well, but still not super illuminative. And so there was definitely some trial and error in getting it to work. Because
was it also kind of loading the data and setting the right, or yeah, okay, same experience here.
Basically, he's trying to.
So it's just say more. Is it the net CDF file wasn't properly, or the files that you were bringing in weren't well?
So for us, the challenge was to map the coordinates properly to your data set. So it was also setting up your cube the right way. When I say cube, it's the X, Y, and Z kind of dimensions, because the way you stack your layers is also the way you're going to feed it then later into X-array, and trying to get that right, and then having the right mapping for then to say, okay, this and this axis is actually lat and long, and here's the data for lat and long, and then be able to do those queries you showed yesterday to say, give me just a snapshot of this little area, for instance. That was the steepest learning curve for me, and yeah, that took almost a day.
yeah, we were doing the same thing. You know, I had the data in NumPy arrays basically from rasters and was trying to initialize a data set, and it's just hard to, the documentation doesn't make it super clear what the arguments need to be and how they need to be formed, and it's actually like kind of picky about ordering of things, but it doesn't make it clear that it's picky about ordering things, and so it just takes some trial and error when you've never used it before.
Totally agree.
Yeah.
Oh, were you gonna start over with X-ray?
I don't think I need the mic. The why Seaborn versus simpler plotting library?
We did it in both, and Seaborn was pretty. Also a good answer.
That was a good answer.
By both, I mean Matplotlib and Seaborn, but I know there's more out there.
This is just a comment on if you scroll down a little bit to your snow depth change maps, or
These ones?
sorry, the ones that were by the different parts of the, or different elevations in the watershed.
Yeah, these.
Yes, I like these maps. I was just thinking that it's, in terms of interpreting it, it's a little bit hard using this, like the Viridis color scheme, because it's not divergent. I assume you have value. It looks like you have values going both directions from 0. So just for my like photographer side of my brain. But I do think that's a cool way to think about, to visualize kind of the different elevation bands. That's something I like. I really like that.
Cool. Thanks.
All right, well, let's thank the Snowmelts group.
That's just well, I just put that, that's what we did. Just introduce what we did.
Okay.
And then I'll switch to your PowerPoint.
Sounds good.
Okay.
It's just kind of...
Yeah.
Ready? Yep. Okay, so we... This is... I don't know. Oh, there. There. Hello? Okay. That helps. Okay, so we're a little bit of a change in direction, comparable to the last group who talked. I think our sort of overarching goals were similar in that we were really looking to learn a lot more about the tools and techniques and applications that we've covered this week. But our emphasis collectively, even though we each had very different sort of takes on that, we're looking at pedagogy. So how to teach others what we do in terms of geospatial analysis. And in that vein, using a platform called LandLab, which is a set of tutorials mostly aimed, I think, at earth science applications, and teaching those kinds of tools and applying these open source approaches. And so, so we can, I think, yeah, see this here. Just a quick overview from sort of the main page or Jupyter notebook that we see that comes up for LandLab tutorials. And again, for earth science applications, there's a whole slew of tutorial applications that they've built. For my purposes, sort of my personal goals here were to look at potential earth science applications. I'm a lecturer in earth and space sciences, so I teach mostly grad level students on what I would deem advanced geospatial analytic applications and approaches. And so I was looking for tools that will help me do this, and in particular teach grad students how they can go into open source tools and resources and get a little bit past Esri and so on. And in particular, since a lot of our students in the department are interested in geomorphology, and in particular, of course, given issues in Washington State, very interested in landslide hazards and kind of hazard mitigation and analysis in general. Looking for applications that are of interest to the students, and in particular landslides. And then for me, myself, kind of stepping back from that, I just wanted to be able to understand all this stuff that we've covered as in the little bit that I could this week, to then be able to pass that on to my students. So what I did was worked on a practice tutorial, actually just basically just did slight modifications to a land lab tutorial looking at a shallow landslide model. This is the infinite slope factor of safety equation that takes in all these geophysical parameters to estimate what the probability of slope failure is in a given location, and using Monte Carlo simulation to do that. And this tutorial that was set up is applied to North Cascades National Park in watershed there. It was originally for Thunder Creek watershed, and to get my practice, and try and cut my teeth a little bit on Jupyter notebooks and their tutorials, applied it to a sub-watershed within that, specifically Fisher Creek watershed. And this slide really just kind of lays out those different pieces that were in there. And essentially what the notebook does is it takes in these data layers and does processing through that. It kind of guides the student through the steps, essentially showing the student the process of those data sets being fed into Python through various geospatial analytic tools, and calculates out these various components of the factor of safety equation, to then ultimately give us plots like this, where we see, for instance, in the plot on the left, the estimated, through Monte Carlo simulation, the estimated slope failures that might occur. Part of the goal of this tutorial as well was to look at pre versus post fire potential for landslide, in particular for probability of soil saturation. So of course fire comes in, knocks out all the trees, slopes become less stable, and then as you can see in the lower figure, the probability of slope failure as a result. And so again, my goal was to be able to have this kind of tool that I could give as a lab exercise to students. It's not something that we could run through in this tutorial, in this presentation, because it does actually take about an hour to run. So that was my approach to this project.
Hi, I'm Rose. I joined this group of developing tutorials because I have previously developed tutorials in MATLAB, and I wanted to transfer my skills to Python, which is more accessible to a lot of people who don't want to pay for a huge MATLAB subscription. So I come more from a geophysics background, and some of my recent research has been detecting blue whales on ocean bottom seismometers. So ocean bottom seismometers are usually there to measure earthquakes, so they're very low, they record at very low frequencies. But some of the large whales basically can call loud enough to make a whale quake, shake the sediments of the seafloor where that velocity meter is resting, and show the whale call signal on one of these instruments. So one part of my research is detecting whale calls on ocean bottom seismometers. I'm not going to be able to get into the details of that during this talk because, like Stephen's, my tutorial takes about an hour to run through, as I found when I tried to help some people run through it earlier today. So I'm going to just talk about basically what I'd expect somebody to get out of it if they spent the hour to go through it. Mine is also on the Git repository, link to it on our LandLab repository, and you can clone it and run through it if you'd like. In my tutorial, we use some scientific methods in Python, NumPy, SciPy, and Matplotlib. We will read audio wave files into Python and then extract the data from that, and visualize acoustic data as time series and spectrograms. So detecting blue whale calls, if you look at these figures, those signals, downswept, 10-second long signals you see, are blue whale calls. They're about 15 hertz. The top plots are waveforms, which is just what your audio file pretty much is, what that velocimeter reads. And the bottom plots show the spectral components of that. So it shows you what frequency those whale calls are at, and how long they last, their bandwidth. And so we use spectrogram cross-correlation to detect blue whale calls because it's more obvious on a spectrogram that it is a call than on a time series. So my tutorial walks through how to make a cross-correlation kernel. Cross-correlation kernels are something that you two-dimensionally cross-correlate with your spectrogram that causes peaks in detection score from your correlation, and those peaks will show you where you likely have a blue whale call. So if you apply it over a very long time series, you get peaks in your detection score, and you can zoom in and look at those peaks to see, hey look, you found some blue whale calls, that's great. So if anybody's interested in signal processing, in signal detection, I really recommend that you look through my tutorial. And once again, this was just an exercise in me developing my Python skills and hoping to be able to share a little bit of what I've learned with you guys. So yeah, next is Helen.
Hi, my name is Helen Duis, and yesterday we learned about S-array a lot, and today my presentation just adapted from Joe's lecture, and a little bit because we can see this is Joe's lecture yesterday, and that's the S-array data structure. We have temperature, precipitation as an environmental variable stored in S-array, and we have a latitude and longitude and time domain here. So for my work today, because lots of people use the GeoTIFF data, and then Joe just demo using the NetCDO file yesterday. So my work here today is using many time series GeoTIFF files and read into S-array data structure and get output as a NetCDO file, and then we just choose a random point of interest to explore the time series information. That's my workflow for a mini project today. And here's some code. First of all, we just define a data index for the S-array, and then we load in a many time series geo raster file. For this case, it's an AET file. It's actual evapotranspiration file for 1980 whole year. It's monthly. And then we just create time and SY dimension for a new S-array. So that's the step from the notebook. And finally, we save it as a NetCDF file format and export it as a time series information for the point of interest from the NetCDF file. So that's a very short tutorial I did for this project. So this is very basic S-array, so if you have any question, we can discuss later.
Great, thanks very much. Any questions for the LandLab group?
I was wondering with your tests earlier in the breakout session, what were the main things that you realized you thought people would get but they didn't, or the simplest fixes that you could make and how that process went?
Well, mostly went through my tutorial, and first of all, it took a lot longer than I expected. I originally wrote it for people who had a background in signal processing. That we had taken a quarter-long class, and then we were teaching each other projects at the end. So I didn't realize how much information, background I had to give before we could even get started. So I would put a warning in my tutorial that, hey, you should have an introductory level of time series analysis, or perhaps you should look at, a link to a previous tutorial you should look at before trying this one. So.
What did you like about LandLab relative to other educational tools you might have used in the past?
Well, from my standpoint, is just the clear level of effort and thought that's gone into it, that in terms of both content and accessibility, just having those resources out there, and related to that, the level of collaboration. So even before Geohackweek, I first learned about LandLab from a former student who is already an expert in it, so she probably could teach me a thing or two beyond even what I learned here. So that definitely was just an amazing resource in that regard in terms of compiling information and knowledge and accessibility.
Thank you. Any other questions? All right, well, let's thank the LandLab group.
Hello, everyone. Our group is called #Popville, and we investigated kind of an issue around interpolating raster counts data while maintaining kind of the same count overall. And so just sort of as a general structure, we spent some time kind of putting together a Jupyter notebook that kind of walks through the problem and implements sort of a very basic solution. And so we're going to walk through that, and then hopefully have a little bit of time at the end to chat a bit about kind of higher level or more spatially useful solutions to this problem. So to begin here, I'm gonna just, to give you a little bit of background, we're working here with two different kind of clipped raster files. One is a population surface from a Oxford-based group called WorldPop. It just reports 1 kilometer pixel population counts globally, and then sort of this mask file that's just ocean and land. And we clipped this down to an area of part of Indonesia between Java and the island next to Java, to sort of as an example here. Possibly.
Possibly Sumatra.
We'll just, whatever you want the other one to be.
So, before we doing any analysis here, we define some functions for the plotting, and this one is for the plotting of the mask data, and this one is for the plot of the population data we have. And this is a function for scaling the color map to make it nicer. So we wrote a function to route the raster data using the library of rasteria, and also modularized with other bunch of functions. And we also did some basic information access from the raw data. We get the longitude and latitude information from the profile, and we also, to better illustrate the issues with the data, we also did some categorization of the two different types of data. So we basically have 4 situations for the pixel pairs. One is the population data on land, and the other 3 are no population data on sea. These 2 are normal, and we don't need to have more processing for them. But the issues are the population data on the sea, and the other one is the no data on the land. That's the point where we need to deal with. So let's first take a look at the raw data. This is a plot of the mask. The light blue is sea, and the light yellow is land. And here is a plot of the original population data, and you can see the distribution here, and it's mostly located at the coastal area. And from the first glance, there's not much difference, but using this plot, we can see the 4 different types of pixel pairs. So the blue one is the light blue one is the no data on sea, and the yellow one is the data on land. The issues are the red points and the black points, which are associated with the no data on land or data on sea. We also did some counting analysis of the different pixel pairs, like the percentage of those points in the data set. You can see the percentage is really small, but it is still important to make it correct. I don't want to hand to David to explain the detail of the algorithm.
So in this algorithm, what we did is we kind of set this up as we could kind of plug in different types of algorithms. So this is the most basic of all the algorithms. And so what the most basic of all the algorithms does is uses the classification to find all of the points that are people that live in the water, takes that collection and then evenly distributes them to people that live on the land. So places that are on land that need data. This isn't particularly accurate, but it's kind of a first step to make sure everything that works correctly. We'll talk in a little bit once we're all done about some of the other things that we're in the process of doing and kind of some future things that we're thinking. Who's next?
I'll talk.
Okay.
I'll talk a little bit about this. So yeah, that bit that David put together, we were able to generate this final kind of new population surface, and so this is essentially aligning our mass data, or our population data to our mass data. As you can see, it doesn't look that different because again, the percentage of pixels that are changing aren't very high. But to get an idea of how to best look at this, we sort of examine the difference between the old population surface and the new one. And we get this figure here, which is essentially showing those pixels that either increased or decreased in population. And so you can see the red pixels are those that we didn't have data for originally, but sort of got apportioned data from the blue pixels. And as you can imagine here, because there are some of the blue pixels had a greater number of population, that's sort of how this scale ends up in this way. You may also kind of recognize that, at least I thought this was interesting, that when you're looking at this figure, you'll see there's a whole bunch of these red pixels along the coast. And when you're looking at this final figure, they don't really show up. And that's not because nothing happened to them, but it's just because those are pretty low population pixels, so the number that gets removed there is pretty small as compared to some of the more urban areas here. And kind of just at the very end, to kind of make sure that we're doing things right, we just compared the sum of the population. Here we had 4 people different. We attribute this to some sort of rounding error, but that's still, whatever, 1,000% of our data set shifted around. So that's pretty good performance. And kind of just at the end here, we wanted to, because we brought the data in as a GeoTIFF, we wanted to export that out again so that whomever was doing this would be able to use it again. And a kind of final point about, we talked about this a little bit at the beginning of the week, kind of the importance of projections and sort of spatial attributes. And because we were using this mask file as our kind of our bedrock to match everything against, we wanted to make sure to use the profile information from that for our new export. And so this last bit just checks that we're using the same profile information. And you'll see that the affine information and the width and height and node data are all the same between the data sets, which is, when you're working with raster data, is something that you like to see. I think we still have a few minutes here at the end, so we'll just hold it to Luke and David to talk about the kind of further direction ideas in terms of distributing the count pixels.
Yeah, sure. Okay, so the one, we have 2 algorithms that we're in the process of implementing. One of them, instead of just kind of aggregating all the people that we have to move, and then uniformly pushing them to the places that they have to go is to use the distance. So for each pixel that has to move somewhere, find the nearest pixel that's going to be there at the end, and then move some of the users over to that. And so the implementation of that is pretty much done. Actually, I think we have two of this.
Two implementations.
So the first implementation that we used of this uses from SciPy. There's something called the Euclidean distance transform. And what this is doing is it's a quick way to find kind of all the nearest neighbors for a specific point. And then the problem with this, though, is it only finds one nearest neighbor. So if you kind of have a tie, you kind of just end up flipping a coin. We have another implementation that actually goes and finds all the nearest neighbors for that specific one, and then can dump them uniformly to the other ones. And then kind of this gets to a deeper problem, though, that we are starting to look at, which a little more mathy. Talk about the math version.
Yeah, so that version, what we're talking about doing is you can parameterize the exterior of each of these. Imagine you have these connected sets in your map of an island. The maps are full of islands. And we can define a parameterized function that outlines the shape of the island. And so we can do that based on the maps, just looking at the boundary. And you can, it's the Fabergé's distance, right? Fabergé, whoops, different kind of thing. Yeah, so you minimize this metric called the Fabergé distance between these two sort of functions defining the boundary. And then that sort of gives you two lists of coordinates that have a one-to-one correspondence with each other. And then based on that, you can define a strain. So you talk about how these island bodies have deformed in the process. And then based on that, you have enough information to uniquely determine with an interpolation algorithm the strain throughout the interior of the body. Maybe not uniquely, you might need to regularize it a little bit. But it's a problem that can be fairly easily solved. And so we're trying to figure out a way to implement it sort of in a deformation mechanics type of perspective while conserving population count. Anything to add?
Yeah, anyway, so obviously there's lots of further direction, and I want to thank all my teammates I've learned a lot of interesting things about this problem I would have not coming in at the beginning. So if you all have any questions? Any questions?
I have a question. I'll just talk here and I'll talk loudly so other people can hear. How exactly did you come up with this idea, and is this applicable in your thesis research, or where did it come from? I'm just wondering.
Yeah, so I work at a research institute. I manage a bunch of GIS data, and one thing that people use for modeling is this world population surface, and essentially everything that they model is built in R, and R is very finicky about rasters being exactly the same and having the same coverage and all this other stuff. And so I've done a bunch of other sort of interpolation algorithms that deal with regular continuous data, but for counts, because we're often dealing with like disease prevalence and other similar things, you can't mess around with the raster values in the same way. You basically have to preserve a sum, and so that's a problem that no one has really been able to figure out, and we want to, so this kind of this problem came out of that. And so it's basically trying to come up with a way to, change the coverage of your data pixels while still maintaining the same sum, and then having your new data pixels maintains a reasonable spatial pattern that, should mimic what they would actually look like.
Afterwards, let's talk. I'm familiar with that problem. Using a higher resolution data set like from Indonesia wasn't an option.
So in this case, there's lots of kind of individual country censuses or other types of data that you can use, but we needed a raster data set, and beyond just that, but a global population data raster set. So this world pop data the data is based on a lot of censuses, but it's in some ways modeled, and so
it's basically to create something that globally is sort of coherent. Trying to construct something that's has different methodologies in different countries doesn't work if you're wanting to look at a global analysis.
All right, well, let's thank these guys for a great talk.
Thanks, everyone.
Okay. Hi, our team is called Tremorvis, and as the name says, we were working on a visualization of a data set. So we have a big data set when you have what is called seismic tremor, and each of them has a time and a location, and we wanted to visualize them on a map. So that was what was done before. So each of the dots is a location of the source of a tremor, and with the color code you have the time when the tremor happened. So we're not very satisfied with this visualization, so we wanted to have something more interactive when you can zoom in and out and you see more what's happening, because the tremor are moving over time, so you want to see the movement of the tremor from south to north and north to south. So we tried several Python libraries. So we wanted to try the library, the package Alter. So do you have opened the, yeah, this one? Yeah. Okay.
So if you haven't heard about Alter, it's a really pretty neat library coming out of work in a couple of different places here at UW. And if you're trying to make interactive visualizations, it's often a place where you can do it really quickly and easily, and it's especially nice with Pandas data frames if your data is in that format. And we wanted to do something interactive, and we knew that there was, on some level, spatial data support in Alter, and because there's some examples there. And so that's what we started to hack at. And we hacked and we hacked and we hacked and we hacked. And I'll let Ariane talk about what she ended up with miraculously.
Okay, so what we ended up is, maybe I should show the final with the big one. Yeah. Can you get me here? So on top here you have the map of all the tremor, and it's color coded by the time when it happens. And on bottom you have a timeline when you have the number of tremors, so you can see check the tremor activities and see that there are big peaks in tremor activities. And what you can do now is you can select a small part of the timeline and move around to see the location of the tremor moving around. So you can see that it's moving, disappearing. And when you are here, you can see the tremor moving. So that's good. The only thing is we wanted to have a background map behind that to see exactly where we are located, because now we can't really see where all this is happening, so it's not bad. But we couldn't manage to get that. So we did a second trial with the bokeh package, but we lost part of the interactivity. We can show.
Yeah, so another group was looking at bokeh as well for interactive mapping, and bokeh does seem to have better support for spatial information, but it doesn't quite have the same, that really cool window that you can expand and then drag across the bottom chart that interacts with the top one in Alter. We don't quite get that, but we can build a little widget here at the bottom, just a slider widget. And you can see as you go through time, you'll see the red dots light up as the tremors occur, and then we left the tremors that had already occurred there in gray. And if I go down here to a place where we get a lot of activity towards the end, and having the two plots together helps you see the peaks. And so if we go to that big peak towards the end, hopefully I can do this slow enough that you can see the directionality that Ariane was mentioning. It's going to go from south to north from here, I think. and you can see it just travel. And not being the domain specialist like she is, that's something that we should expect to see, and that's something, the nature of the fault there, the subduction zone or something, something like that. That's really cool to have that as part of the visualization, because that is really part of the phenomenon that we're measuring or want to represent. Yeah, do you want to say something about some of the nice things about the approaches of Altair is if you look at the number of lines of code that you have to write to get 2 plots with interactivity, with tooltips, with a legend. Good luck doing that in any other visualization library with just, I don't know how many, 20 some lines of code probably. So there's some real advantages there. We did find that there are ways to hack a topo.json file in a vector format into the background, and that's what it seems like those background files are. But it's still very, very finicky when it comes to that sort of thing. So Altair is a quite young library, and I'm sure that the brilliant folks here at UW are already working on adding more geo support to things like that. So yeah, just to give you a sample of some of the tools that are out there and how you can make things interactive and move around and do cool stuff. Okay.
Questions?
All of your points were the same size. I'm wondering, did you have a sense of like the magnitude of the tremor or some other variable?
No, we don't really measure magnitudes. That's why we kept the size and we didn't try to do something about that. Maybe we can do it. Yeah.
We could definitely encode that information. We had a depth variable for each of them, which might have added more. What it ended up doing was slowing things down the more encodings that it had to represent. And actually the points that you see here in this one is just 25% of all of the points that we had. We had something like 28,000 points, 28,000 records of these small little tremors. And so, you know, you're way past the limits of when these visualization packages are really built to do interactivity. But yeah, you could easily encode lots of other variables. Both Altair and Bokeh, to a slightly lesser extent, are pretty open about how you're encoding that information, and makes it pretty easy for you.
I was wondering, I'm not sure if you guys would know, but does anybody have much experience in 3D plotting in Python? And is there a way that's easy, or what package would it be to start with, or anybody?
There is no Miami. I know Quadly has one package for Python and another one for R. Have been using that one for a long time, and I kind of like it. It's really convenient and highly. I would recommend that one.
It depends also on what kind of 3D information we are wanting to plot, you know, like if it's more analytical, or there are other packages. There's something called MayaV as well. I mean, or you can actually then go into another package that is developed by, I don't know, one of the research labs, which is ParaView, which actually has also Python, you know, API, and that offers, you can visualize tensors and all kinds of stuff.
And most of these, I guess all of the interactive ones, like you can see the one on the screen there, they're all wrapping JavaScript libraries.
Do you plan to communicate any of this to the Altair developers in the future?
Yeah, actually, in the middle of the week, I tweeted at Jake Vanderplas to see if he could give me some guidance. He basically said, nah. That there wasn't really any support for that. But yeah, I want to try to dig into it a little bit and see where there might be room for that. And I know there is, or I've read, I guess, that there's some interest on the Vega Light team to add more geographic support to things.
Any other questions? Really cool stuff. Thanks a lot. Let's give these guys a hand.
Hello, we're the GeoAffinity group, and our project was to provide context for geospatial inquiry, comparisons, and search. So we started off with 2 use cases. One I brought with me here, which was from the UNHCR, which was to, given an area like a refugee camp, superimpose or enable comparison of that, the differences with where somebody like would live in the United States. The second use case would be like a science team. If you're studying in boreal forest, near a marine environment, etc., that you would be able to locate other places on the planet where such things are occurring. And there is already an organization, Globe, out there specifically dedicated to that purpose. And so our method was basically to take an 11 by 11 kernel centered on the area which encompassed the object of interest, and then take basically a histogram, statistics of what occurred. On the left there is the different sorts of land cover. So the second part of that is the boundary of that area needs to then be placed onto another location on the Earth's surface. And so my part of this was to find data that we could use. And I started out hoping that there would be some really simple Python accessible API that we could just go out, snag the data, and bring it down. Not really the case with these data sets. They haven't matured yet to that point. That's why I asked the speaker of the lecture the other night if there was available. Then I looked into using the Google Earth Engine Python Access API, and I think the first line is, "This is not trivial," in the description. And so then I looked at the GDAL WMS capability to call from the API, but it ended up that unless you're that server where the file is located is set up in a certain way, that wouldn't necessarily. So we fell back onto the download it locally, and then it was still very, very large. In the upper right-hand corner, it's basically the whole world. So I took that and just made most of it, blank space to test the algorithm. So we use this ESA land cover CRDP data set, and I basically used raster IO to pull in the information, display it, and my initial pass was I was very excited about using Xarray, but then after I had a conversation with the presenter, I found out that Xarray, not a number, isn't, it still occupies space. So in a data set this large, it isn't just the land cover data set, it's all of the things, potentially 84 layers, hundreds of layers that need to be compared. So I'm back to the drawing board on that. And so now I will pass it off to
kind of the heart of this geoaffinity concept, you need to be able to move a shape across the surface of the Earth preserving shape and area to kind of give the person an idea of like how big something really is. So here I'm kind of scrolling through the meaty code that does this, utilizing GeoPandas data frames. And so this first plot is, so we're using a Juba refugee camp in South Sudan. And yeah, this first plot is just a lat-long plot of the shape of that refugee camp. And then this home boundary, this plot is then translating that shape onto centered around a university district. And this is still lat-long plot, but you can see kind of distorts in these dimensions lat-long, but that's to preserve the area once we get it onto like a 3D map. So these are the same shapes plotted on Google Earth. So this is the refugee camp. And then these are the translated coordinates from that original shape to centered at the university district. And as you can see, the shape, it's a preserved shape, and you can't see here, but Google Earth allows you, you can calculate the area of the polygon, and it turns out that the area is preserved as well, like down to, size of these are like 2 million square meters, and I think it's like plus or minus like 1,000 meters off. So, so that's helpful if you're familiar with university district. You can see the span, but not everyone, I guess, in this room would be familiar with that. So there is just a simple web application. If you do want to check it out, you can just go to that URL and yes, using state-of-the-art web programming principles. Yeah, I mean, you input like a central latitude, longitude of, I guess, a place you're familiar with, and it gives you that shape, and that's the same area of this Juba refugee camp. So this is centered on where we are right now, and you can see how, just from this map, I mean, this map is interactive if you do want to zoom in and stuff like that. But yeah, you can see, I mean, a red square covers all the athletic facilities, goes across 5. So, I mean, that gives you an idea, I mean, because if you know this location, you know University of Washington, you realize how big the refugee camp is. So, yeah, you can go ahead and play around with that. That's the URL, anyone can access that. Going back to this, let's see, I don't have a lot of time left on mine. So this is just the math behind it. These are just how I've never actually worked with geospatial data before, so I thought this would be more trivial, just move this shape over here, what's the big deal? But it turns out you have to take a lot of stuff into consideration. So there's just the goal to preserve the area. It kind of just is just to keep consistent, I guess, the arc distance between the center of your shape and each point around the polygon. So yeah, these are just kind of schematics. This is how I thought through it, and utilized the great circle distance equation, measuring distance between points on the surface of a sphere. And yeah, that's the math behind it. And now I will pass it off to Nathaniel.
Thank you. So most of what we've been doing has been covered, but I just wanted to speak a little bit to my journey as someone who has very little technical expertise in this area. So I took the part of taking this transformed shapefile and just putting it in a map, simple as can be, or at least in my head I thought it was, but I still ran into a whole lot of trouble, and I want to actually speak about that. So first thing was like importing all the relevant libraries, Folium and GeoPandas, and I just wanted to make sure, okay, I can create a map. Good, we're golden. Then it was, okay, can I put a shapefile on this map? And I did it, and it took forever. Yeah, but I eventually did it, okay. And then I was like, okay, how about, can I do this with a properly transformed shapefile? And I couldn't do it. And it took forever, and it was because I needed to actually specify, this is the new type of projection that we're using, Folium. Please help me with this. And I also put in this little screenshot of me making sure the shapefile actually worked. I put it into Google Earth to make sure, okay, this shapefile is working. Yes, so what's your problem, Folium? And I eventually figured it out, thanks to our wonderful people here. And I just wanted to speak about a couple things I learned during this process, that there's a lot that can go wrong, even in the very simplest of steps. I learned the importance of good documentation. I got very good at Google and reading documentation, and I think that's one of the most valuable skills I'm going to take away. And also the kind of limitations that you can impose on yourself by thinking in the boundaries of like your own personal experience. I was set to just create like a JavaScript web application, like just do some Google API stuff. It'll probably work out, right? Not only is that going to be very difficult to do, but it doesn't really test my knowledge. So I chose to do something much harder for me, which was to use these new libraries that we've been working on here. That's all I have to speak of. Thank you.
So, speaking to the experience level, when you came in, how would you rate yourself in terms of geospatial?
Oh, I had absolutely no geo experience. Yeah,
so did you even know what a projection was?
No, I learned all about all the projections and how,
so,
it's not really exact.
So with the the various tools, so you had Notebook, the Jupyter Notebook available, Google Maps API, and then the other Folium. So how did you decide, as you were working through, how did you decide which one to use?
It was basically like I did all of them, and when I got far enough that I realized, wait a second, this is going to be actually very difficult. And then I move on to another one and moved a little bit in there, and I was like, okay, this is going to be difficult, but it's my fault. So that's kind of my logic.
So one of the things that I found, I've been doing geospatial stuff for a while, and how the world has changed for me is it used to be that I could be like good at ArcGIS and understand how to find data. And this week here has exposed every one of my current frustrations with the world. Is the data is no longer local, right? It's all out there someplace. To process it almost is required that you do remote processing. And so my previous pattern was of kind of islands or peaks of desperate, narrow expertise where I would learn how to do something, get it done, and then not even really understand why it worked. And then for 6 months, there's a long, slow valley of not working with it. And over that year or whatever, the technology marches forward. And this just got worse and worse and worse. And what I really loved about this place is as we're in the lecture, the application presented itself immediately to a problem we had with the project. As X-Array appears, the various visualization libraries. Would you like to speak to your experience?
Oh,
yeah. Here.
Oh. Yeah, I think we're done. We can take questions if you guys have any.
Yeah.
Any questions for these guys?
I have a question. Oh, I'm sorry.
I'd love to know really how the extent of that and how big it is. And it's supposed to cover Texas, isn't it, in scale?
Yes.
Yeah, no, that's, we would just need a shape and you can translate that anywhere, so, yeah.
Because I was in a newspaper article, you'll see, this is an island the size of Manhattan, or that's 2 football fields large, or this country's the size of Texas, right? Because people want something familiar that they can do that cognitive comparison with.
It's always the state of Rhode Island that gets chosen out of field. It's like equivalents of that. Well, thank you. That was great work. I really appreciate the way you guys spoke to sort of the process of your learning this week, and we actually are listening, and that's great for us to hear as well. So thank you. Let's give these guys some applause.
Is to build a web portal for inland water CO2. So the ultimate goal is we build an interactive front-end and back-end utilities for the web portal. But it is just another project that can be done in a week. So we just list our goals for the Geohack as follows. First, to create a relational database based on our current data, and second, to load data to our database model, and 3, to create static and interactive maps to explore the data. And my group members have really cool stuff to show you. So Ran will present on database model and data loading. Elena on interactive time series, and Wei Shi interactive marker clustering maps, and Catherine, I think, we present on some exploratory data analysis. But before that, I just want to acknowledge their hard work. They are really hardworking and smart people. Our team group members, Elena, Weish, Catherine, Ron, and me. And also thanks to our Geohack tutors, Don, Catherine, Liu, and also support from our PIs, David Butman from UW and Pete Raymond from Yale University. And also thanks also to eScience Institute who kind of bring us together, and also Yale School of Forestry and Environmental Studies, and NASA's Carbon Cycle and Ecosystem Division who funded this whole CO2 project. Okay, thank you.
So I'm Ryan, and I was responsible for our back-end implementation of our project, and with a lot of help from Don, a lot of help from Don. So our dev stack consisted of having a Docker container with a Django web framework and Jupyter notebooks all installed inside of one Jupyter inside of a Docker container. So what that allows us to do is, just to kind of show you, there's a bunch of like screen dump here, is when we start our Docker container, it goes and builds everything Docker for Django, Docker, the virtual environments for Python, and Jupyter Notebook, goes and starts it, brings it, this one. So, and initializes all the scripts like from the get. Oh, we ran out of room. So this, and a PostGIS backend for our database. So this created a PostGIS, downloaded and installed PostGIS into a Docker container, started it, created the web framework with Django. We then used some Python scripts and load the data directly into it on startup server. So this reads data down from an Excel spreadsheet and then inserts all the data into the database all in one sweep. You say Docker compose up and build, like it goes and does this all. So that's awesome. And it also, we are starting our Jupyter Notebook from the same Docker container. So, where did I? Sorry, I'm not a Mac user. So in our data implementation, this is our script that I wrote to be able to load our data. We are reading the data in from a XLSX file and reading it into a Pandas data frame and doing some data cleanup and being able to iterate over the data frame. So we set up like a database connection, and this we are writing straight SQL to be able to insert and iterate over the data frame after we've cleaned it up and then load it directly into the database, which you see all that junk that got posted out with the Docker container started up. So that also, then, that's not it. So Django then lets us create a cool admin interface to be able to interact with our data. So this is actual representations of our data tables. We only did model 2 of our the tables that would be there. So this is all 2,000 samples that have been loaded into the database, and the fields where the date that is formatted weird, and then a actual point representation of our point and a PostGIS geometry representation, and that's supposed to be a map that you're able to go and edit. And this is all like live, so you're able to save and add records or edit these records from this interface here. The last part is then I was able to read this back out, where if we take the URL, I created a data point to read it back out into a JSON representation format of everything combined all back out. So this would then be the endpoint that you would read into a web mapping application or into other Jupyter notebooks or everything, using HTTP requests and web protocols rather than loading from a file. So that's my responsibility for backend.
Great, thank you. Hi, I'm Elena, and I was part of the visualization side of things. So if we go back, let's see. Here, interactive time series. So what I really wanted to take away from Geohackweek was to get a kind of a better idea of how to use Python for visualization, because for the most part I program a lot in MATLAB, and I've done some work in Python with pandas and stuff, but as far as plotting, I know that Python has some really cool ways to do that, but I hadn't really explored it yet. And so you can see at the beginning here, I'm not going to go through the whole notebook because it's kind of long, but the beginning, we're just loading libraries and data, and then we had a very beginning script called loaddata.py, which everybody who made a notebook ran that script, which would initialize the database for us, which we were temporarily working with before we had the back-end development fully completed. So now that that's completed, we probably won't be using that anymore. But as we scroll down, you can see we have CO2 site locations. That's the data that we're working with for this project. And we started out with a first map, kind of visualizing the locations of our CO2 concentrations or measurements, as well as CO2 flux measurements, specifically focused on North America, just so that we could get it plotted without Jupyter crashing on us. So you can see here that when you click on a point, it'll tell you the type, I guess the source of the measurement, as well as what type of measurement there is and how much measurement there is. So CO2 flux is in blue, purple is regular CO2 concentration, and then the one red point was that we had data, but not all of that. But we had a site measurement, but we didn't have data that was readable to us. And so moving on, I went all the way past it. What I really wanted to do was kind of look at how to plot an interactive time series with this data to see how concentrations maybe changed per site over time if we had that sort of data available to us. And again, I won't really go into detail, but because we are working with a very large data set, and the goal, in fact, of this project is to be able to have a web portal where people can actually contribute in the future with their data sets. Not all of the data that we have is in the same kind of format, especially like the date recording. For example, some dates were missing, some dates were just in year only for measurement, and some dates, had the year, month, day. And others were actually in a completely different format that we didn't really recognize. So, of course, when dealing with a lot of data, you kind of have to, from multiple sources, you have to take that into account. And so we had to clean up the records a little bit, and then just for this exercise, we only took a subset of that data. And to make this time series, I was intent on using Folium, so I found something called TimesLetter Choropleth, which I used, and there's an example of how to use this if you follow this link as well, which now that I've seen some of the other presentations, I feel like there might be better packages for what I did, but I already did it, so I guess I learned. So I'm working with data from 2004 basically to 2006. And so basically what I do is I tried to, for this time series with this plot, is to map out concentration values over time where the marker color is dependent on the amount of CO2 measured at that particular time. So if there's no CO2 measurement for that time, then the opacity is set to 0, and otherwise it's dependent on the concentration measurement. And so you can also see I did something kind of weird here when I'm kind of setting up the dictionary for this plotting. You can see our point values, or our values were recorded in points, and I had to change this actually to a polygon. So that is because I found out while working with time slider choropleth that in order to change the marker color values, in order to simulate changes over time, you actually have to work with something that's more regional. You can't work with a point because it won't recognize the color values, or at least I tried really hard to figure out how to make it do it, and I couldn't. So that's why you can see this like transformation to a polygon. It's really not, it's not real, but I had to do it to be able to make the plot. And so you can see we've got a mapping for a color based on our concentration, which I then map to an actual color map. And then you can see the results here, where color changes over time for different locations, all the way up through 2006. And so you can see maybe for this data set that this isn't like, maybe possibly the most exciting thing because we don't have as many records that repeat up at a particular site over time. But definitely thinking long-term, as people add more records to the data and to the web portal, this type of analysis might actually be kind of useful. And also, just as a side note, because I don't work with CO2 data at all, when I finally got this plotted, it just struck me that the measurements, especially as you can see along this region, move along the river that you can see there, and I got really, really excited. So anyway, I had a good time. Thank you.
Okay, so hi everyone, my name is Wei, and my task for my team is to make our interactive map a little bit prettier with master clustering. So what does that mean is, there's some overlap. Oh my gosh. Okay, so if you still remember yesterday's tutorial, when we visualized the map with the markers, so what Tony showed us is only like 3 or not that many markers. So on the map, it will show clearly where is the marker and what the marker looks like. But for our case, the site location of the CO2 data collection, we have a total amount of over 4,000 data points, and we will have more for in the future. So in that case, if we mark the site location like this way, like mark every points on the map will look a little bit overwhelming. Like what's in Texas, we can see there's a lot, but we cannot really tell like what's happening there. So what I did is use a plugin, volume plugin called Marker Cluster to cluster cluster the markers in regions where it's concentrated. So let's take a look at these North American ones. So compared to the upper ones, we can see the marker cluster map will give us a much clearly view. And when you zoom in, you can see the actual marker of each. So this plugin will give us a more handy way to control how to visual the interactive map more easily. Yep. Yeah.
Thanks. I think that's our presentation.
Here, I'll say one more thing. And so one thing, if you guys go to our Docker, our GitHub repository and you have Docker installed, you can go and build this entire sort of image and run this whole entire application on your own machine and have it go. I won't offer to help you install Docker, but you can do it. So. Any questions?
Yeah.
I'm very
Stand
worried.
by.
Very worried about that.
Should I go ahead? Okay. So this was the most amazing team that I have worked on, maybe ever. And so here we are. There's a picture of us. Thank you to all of you for your contributions. Everyone was really enthusiastic and just dove in, and so it was awesome. The problem that we were focusing on was exploring and comparing a variety of machine learning approaches to land cover classification in the coastal realm. And this picture is actually from a USGS study in Puget Sound, but that's the type of thing we want to come up with, these nice big polygons for different substrate and vegetation types. And the location of interest was the Oregon coast. The data are color infrared and natural color aerial photography, as well as a digital elevation model. And for the methods and tools, we kind of had two parallel tracks going. There were a bunch of Google Earth Engine enthusiasts and some Python scripting enthusiasts, and then there were, of course, some crossover as well. So I think, and as far as what I had to do was mostly just cheering people on, and because I'm the domain expert, I spent my time in the evenings making as many training sites as I could, so these guys would have some good training data. As we know, that's critical for machine learning.
All right, so the first thing what I mainly worked on was the initial, is there that link there? Yeah. Oh boy, there it is.
It is over there.
Oh man, that's so fantastic. You showed me that earlier. Okay, so this is, it's about, what, a 10-mile stretch of the Oregon coast by Coos Bay. And so the first thing, of course, was to get all the data imported into a format and an interface that we can actually start working with it. And so, and this was, I've had a little bit of Google Earth Engine exposure, but not a lot. And so a lot of this for me was increasing that knowledge and how to actually work with the files. So it was, I discovered, for example, that you can upload mosaic or tiles of geotiffs into Google Earth Engine, and it'll automatically shove them all together into a single file. And it's super easy to then clip to polygon shape files. And this it sort of largely speaks to its ability to ingest large data and then just flex its cloud muscles, and then suddenly you're able to manipulate and work with your data. And so we were trying to re-download it, and it was becoming this multi-gigabyte file. But we were able to speed through it inside the Google. And so I just wanted to quickly show you some of the images that we generated. And so I was given 2 3-band geotiffs and the digital elevation model. The geotiffs are at 0.5 meter resolution. And so we were able to composite the geotiffs together with the digital elevation model into a single 5-band geotiff clipped to the polygon just of the coastal area that we have of interest, with just a few lines of code. And we can share this, but I'm not sure if it's super interesting to go through all the code. But this is just adding the map layers, clipping all of the different segments of the geotiffs into the same shape, and then stacking them together. Okay, thank you. And I used the points, the training points from Allison, which was 1,400 points across the different classes, and just quickly ran through things that I just wanted to show you something like the CART classification, the classification and regression trees for machine learning, which is this classification, the support vector machine classification, and a random forest classification. And what's less important to me as far as the accuracy is the ability to just flip through these really quick and classify this giant data set rather rapidly. Another person who was working with the classified data, I will hand off to now.
So in a very similar path to what Jonathan did, Okay, cool. So basically what I tried to do was to divide the different classes that we had, and in this case I created some polygon shapes. So if I remove completely the classification algorithm, you can see the small polygons in the center of the picture. So this, for example, is marine vegetation, and these are rocks. And in a similar way, we're divided between trees, the water, and unconsolidated sediments. So running the algorithms, we used CART, random forest, and SVM classification. And the CART classification was a bit more noisy, but it kind of it depicted in a very simple way and quite fast forward way with Google Earth Engine the different environments. Like for example here the trees are shown, and it's able to distinguish between the marine sediments and the water and the rocks. The rocks are depicted as gray. The marine sediments as a light green, and the forest as dark green. And it looks like the random forest classification worked the best way in both cases because it had the less noise, and in some cases it performed better for the habitat classification. So, maybe it's your turn. Okay. You can handle.
Yeah. So what we just covered was supervised learning within Google Earth Engine, and what I have to present is that on the first day when we gathered the group and we had this data, we have to solve this problem. At that time, we don't have any training data. So what I did is that I first tried out with unsupervised learning, also within Google Earth Engine. So it is also really easy, just one line of code within the doc, cluster.vector k-mean clustering, and with that I was able to generate this map. Basically different colors. So first we don't look at the point yet. So the point are labeled data. So first I generated those basically polygons, the rasters, using unsupervised cluster. What it is cool is that it can run without any labeled data. And also it allows us to make many clusters because supervised learning generally are limited by the number of data you have. So that's what we got. So that's very exciting, and we created 50 clusters using this, and we did a visual check. First is that we found out marine vegetations very easily got confused with shadows by the trees. So we increased the number of clusters just so that we get to the point where we can distinguish these two classes. And eventually, Allison created 1,400 points as our labels. So these are the colored points that you see here. And I was thinking that now we have the clusters using unsupervised learning. We have some training labels. So maybe we can put this unsupervised result into some use. The way how I do it is that I still will basically using each of the point, look up which segment it falls on, and then using the segment, I can create a lookup table to say, for this type of color on the map, what class does it represent? To do that, I did it in, so first I did a spatial join within the Google Earth Engine, and then I moved on to Python to do it. The first thing is that I divided data into 80-20%, and still I want the full class to be more evenly distributed within this divide. And it looks like test training and testing have fairly evenly distributed. And then the next step is how to create a lookup table so that for each of the segment I can know what class does it represent. Because we remember we have 50 segments, 50 type of segments, which is way more than the class we have. So what I did is that I basically find the majority of the for each type of the segment, find the majority of the point within it, and created this dictionary, lookup dictionary. Along with it, I also created a confidence score, which basically says how confident we are that this segment represents rock instead of trees. And here is the confidence level, which is calculated basing on the number of points divided by the total number of points. So we can see that many of them have like 100% accuracy, while the low accuracies are around 30%. And using this lookup table, eventually I generated the confusion matrix using unsupervised learning. And overall looking, it looks pretty good. And the overall F1 score is 0.72 for the testing set and 0.7 for the entire data set. And I will hand over to Mia.
So as Jonathan was saying, a really cool thing about Google Earth Engine is that it can take in a whole lot of data and mush it together for you and make really awesome, huge data sets that you can compute on really fast. And you can also do all these really fast unsupervised and supervised learning methods in Google Earth Engine, but a downside to that on the same note is that when you export data, it kind of tiles them down for you, but it also ends up being really, really huge files, especially in our case when we wanted to use these 5 different bands of information. So we started out with red, green, blue, and then near infrared and DEM, and those were all separate files to start with, but we were able to mush them all together to make a 5-band gigantic data set, and it ended up being a huge, huge file that we couldn't easily load into Python. And for our next section, Patricia is going to tell us about some really cool supervised learning she did in Python. But in order to get it out of this really cool TIFF format, we had to use some GDAL magic, which was really a really cool learning experience for me. I've never seen GDAL before and not really dealt with these huge data sets. So we were able to run a GDAL to convert into all this nice little described thing here. I'm not going to really go through it because we're running out of time, but I'm going to pass it off to Patricia, and she's going to tell you about the breakdown of these really quick algorithms we did in Google Earth Engine in Python, where you have more control of each step that you go through.
Sure. So, well, my friends were running this on Google Earth Engine. I wanted to work on my laptop, and then Alison passed me this amazing set of 1400. We were calling it training set, but actually I just split it in two. Like the 20% of that set is going to be like the testing, and then 80% is going to be the training. So I'm training with 80% of 1,400,000 points. And the other thing that I wanted to mention here is that we have 4 classes here, 4 classes for classification. The first class, for instance, is quartered. The second class, so I have it here, rock. 3 unconsolidated, I didn't know what was that. Alison educated me about that. And the 4th one is marine vegetation. And then you can see here in the diagram, like in this histogram, that is well balanced.
which is not the case for most of the time, to work with nice balanced data. I think that was a good start. And then here what I did, well, I'm just showing, I don't see well this formula on your laptop. Okay, so what I'm gonna say right now is gonna resonate a lot with the machine learning tutorial that Shay and Bernice gave you, I believe, Tuesday and Wednesday. Okay, so that's gonna sound pretty familiar for you. And then here, I want to talk a little bit about the metric. So the metric that we use here to test the accuracy of the machine learning algorithm, or the classification algorithm, is the F1 score. So here I'm defining the recall and the micro average here on top, right? It's a quotient of true positives. So I'm using like the definition of multi-class in our case 4. So the first result that I'm going to show you, and my code is available on GitHub,
you want to go up?
the group. No, yes.
Yeah.
So this is the, sorry, the scale is a little.
Which part? Confusion
Yeah.
matrix?
A little bit on top. See, because I want to do.
Okay.
Okay.
To go to the wrong thing.
Okay.
Nope.
How I do
What do you want to look at?
This one.
That
This
one.
picture.
Okay. Got it.
So the first one that we analyzed, I focus on 3, on comparing like 3 different methods, classification methods, supervised learning. So the first one was the k-nearest neighbor classifier, and then unfortunately I don't have time to explain what is k-nearest neighbor classifiers. This is just an example. The picture shows you an example when k equals 3. It's simply like voting, right? So here is the confusion matrix. So this was shown by Shay and Bernice on Tuesday or Wednesday, exactly. And here, really little, you're gonna see on the bottom the accuracy of the. Oh, this is a little flipped. No, this is not the same. Let's go. This one. A little bit. Okay. Okay. Random forest. Okay, so random forest. I'm going to show you first random forest. So you can see water is not that bad, right? So the true label, right? And the actual label, like the actual classification, real classification is in the y-axis, and the x-axis is the predicted label. So we can see that at least water and the vegetation did pretty well in this case. And the accuracy in this case is 86%, okay? Then I'm going to show you what happens with the neural network, because I use like the simplest neural network that you can find, the feed-forward neural network. So the green points, the green nodes that you see here is like that's going to be the input layer, and the middle, the points in blue is what you call the inner layer. So this is a simple single layer neural network. In our case, we use 2 layers, but you can pretty much play with the architecture of the neural network and add as many layers as you want and obtain different results. In fact, it's magic. You don't know what's going on the inner layer. The inner layer, you can impose the dimension of the inner layer. You can impose the number of inner layers that you're going to be using, but you don't know what's going on exactly there, right? It's more than it's an optimization problem, and you're using optimal weights, right? And the output is going to be the classification. It's 1, 2, 3, and 4. It's going to be the classification. So you see now the confusion matrix with that 2-layer neural network. And guess what? If you can see here, now go on top. No, I don't want that number. Yeah, I don't want that number.
Running out of time.
No, but I need to show the punchline. Okay, my punchline is this one here.
Okay.
The punchline, okay, that's going to be 92%. So what I'm trying to do here is to sell neural networks and the potential of deep learning into these problems, machine learning problems. So, yeah.
All right.
Fantastic.
Give me that. Oh, sorry. So that was our parallel lives for machine learning and our LiDAR selfie.
Yeah.
Sorry, it went a little long.
We started off with 7 people and 4 left. So I hope that doesn't say anything about my project management skills. And for those who have watched, the program with Alan Sugar, gosh, what's it called? The Apprentice, I think I definitely would have been fired by now. But nevertheless, here are the survivors. They didn't just leave the project team, I would say. They actually left the Hack Week, so it must have been, I don't know what happened. But anyway, so we did some fun stuff, though, between the 3/4 of us that were left. We also had Ian, I should say, but he had to go at lunchtime today. The problem, if you remember from, I don't know those of you who saw the poster that I presented on the Monday evening, but we were trying to find the relationship between mental state sampled using an app and the built and social urban environment. And we had a lot of discussion about exactly which aspect of the data that we're going to look at. But we decided to focus on 2 things. Firstly, using raster data to look at NDVI and see if there was any relationship between the difference in normalized difference vegetation index in space, which gives you the amount of greenness and mental state, and then also OpenStreetMap data. So originally we had planned to build a big model with lots of features, and of course we had great ambitions, big vision, and it all turned out to be much more complicated than we thought, but we did make some good progress. So I'm going to hand over to Tianxi and Eddie, who are going to talk about the OpenStreetMap data. Yeah, what would you like? Would you like the slides? That's here, yeah. Okay, you start with that one, yeah. Let me get rid of this, it keeps... There you can see it.
Hello everyone, my name is Tianqi, and for our project we want to understand the relationship between social urban environment and people's mental health. So for now, Lucy has the data for people's mental status, and we still need the data on urban environment and urban infrastructure. So we looked at our OpenStreetMap Overpass API to see if we can get something we want. So this is something new I learned through this week. And first, let's take a look at the OSM data. It has 3 basic components, which are nodes, ways, and relations, and we mainly focus on nodes, which are defined by its latitude, longitude ID, and most of them have some tags about their physical features on the ground. And then we need to know the nodes for its tags, as a tag consists of 2 items, a key and a value, and for our project we mainly looked at 2 common keys, which are amenity and natural. For amenity contains like schools, libraries, benches or bars or cafe, and in natural we can get some vegetation like trees, and sometimes it has more specific attributes like if it is an oak tree and or other species. There is an overpass turbo to query the nodes for whatever you want, and you need to use a query language, and you can use the turbo to interactively to evaluate your results here. Yeah, there is an example, and if we run the example, yeah, there are some small blue dots here. It shows us the drinking water places in the box, and we can also query in a certain area you want. Let me see.
Do you want me to hold the mic while you type?
Oh, yeah.
That might be easier. It's probably just worth adding that this data is really, really noisy. That's one thing we discovered. So she actually gave the example of trees. So there's this natural tag that has natural tree, and then some people go and add, further tags, so oak tree, and then sometimes a Latin name of the tree. I mean, that's just one example. And there are, there's huge amounts of points across London of trees, but they're tagged in a almost completely random way. So the only thing that there is really any agreement over is the first level tag, which is natural, and then the second, which is tree, and then everything else is just totally random. So that actually makes the data really, really hard to work with. The other thing we did, which was quite fun, is we looked at the locations of bars in London and pubs, and that came up with a point cloud that pretty much covered London. There was no space left, was there?
No.
Yeah. So this API is actually quite hard to work with. You're basically running, you're running JSON queries, and if you've never written JSON before, that takes a bit of learning.
So we want to see all the bars in Greater London area, and we just query.
So what we were trying to get out here essentially was, first of all, a point cloud of all of these locations of features that might have some implications for health, and then find some way of binning them, which we haven't done yet, but we have some ideas.
So were you thinking that bars were good for health or bad?
Well, maybe a bit of both actually, because there is research to show that entertainment, enjoyment, sociability actually is good for your mental health, but clearly too much alcohol is not.
Yeah, so here we get all the bars in Greater London area. It shows in the box, and you can query anything you want. So then, after we figure out how to use the API, we can move to use Python to get the resulting query. Here.
Do you want us to show the notebook?
I just get some screenshot of some little scripts. We used request and JSON and NumPy package for the query. And first we query the natural so here is to get the data of all the nodes, and from the data we can get the latitude and longitude of all the nodes. And then we can just plot it in the figure to see what we get. Yeah, that's basically how we. Yeah. So.
There's one thing we need to talk about is a projection method. This one is a normal or the standard way, but I think over the map we use another, what's it called, London?
So British National Grid.
Oh, you want to say it?
British National Grid, which is EPSG 7405.
It's a long name, and okay.
With height projection to be precise, because there are two.
Okay.
Which notebook do you want? Which one do you want? Do you want the? If we go to, do you want the OpenStreetMap one? Do you want to look at this one?
Mine is this is INS code.
Oh, that one's INS. Okay.
This is the same one.
But do you want to look at the the little map with the hex bins?
Oh yeah.
What do you want to look at?
Probably your version.
Yeah. Yeah, because I don't think we've got mine pushed, have we? Okay, so it is that one, which is already open.
I think it's already open. I just opened it. It's pretty bottom.
Yeah, there. Can we make that a bit bigger? Yeah.
All right. So this map I created use a hexbin function. I plot in. So we have a data set of like 9,000 records, probably 1,000 for the London area. And we plot in the data, and we created by the plot with a hexbin function, and it just, I guess that's it.
Yes, yeah.
Yeah,
So,
that's it. Yeah. Do
Yeah, so I think what we're trying to get at here is if you can imagine you have all of the natural features and you have a point cloud of those, and then you have a completely separate data set, which is the urban mind data set, and you're trying to find the number of natural features that's within, let's say, a certain distance of a point. If you're going to do that for a huge point cloud, let's say of 80,000 or 100,000 points, one way of doing it is to draw a buffer around each of your urban mind data points and then count the number of other data points that sit within that buffer. But that's going to be a massively computationally expensive thing to do because you're effectively doing a point-in polygon algorithm for... Did I just switch that off? Yeah. Okay, just one swap. Is this on? Yeah. So effectively what you're doing is you're running a point-in polygon algorithm 80,000 times on 1,000 points. So that's 80,000 times 1,000. So there is a way to do that, which is basically binning the space. So you could use a square grid or a hexagon grid or anything that tessellates. I discussed this at length with Jane to find ways of doing it, but it turns out that there is this thing called R-tree which can create spatial indices. So once you've created your grid and you've divided the space and spatially indexed it, doing those sorts of computations is much, much easier, but we didn't get that far. I'm going to show you just really briefly the other thing that we did with NDVI. So we followed the tutorial for NDVI, and two of the people in the group who've now who left halfway through the week because they had work commitments help with this. So first of all, we found a satellite image of the UK. So that's from the USGS Landsat 8 collection. Downloaded the 3 files, so the band 4, band 5, and the BQA. Plotted this data, so there is the red, and there's the near infrared, but obviously showing that you can see it visually. Calculated the NDVI, and then you can output a TIFF file. So in some ways that's the easy bit. The thing that took a little bit more work was then, if you imagine you've got this raster file that has all of your NDVA points in, you need to be able to match the locations where you've sampled mental states and match those to an NDVI value. So the bit at the top is basically just sorting out the urban mind data so that it's, you can do stuff with it. And the magic really happens in these 2 lines here. So first of all, there is this amazing function in Rasterio called .sample. So you have to give it some kind of open raster file, and then there's a .sample which takes some point tuples, and basically what it will do is do the equivalent of a spatial join, but in a really computationally efficient, very, very quick way. So that was amazing because there could have been a huge amount of fiddling around if we didn't have that. One of the complexities is the fact that I'd already transformed the urban mind data to EPSG 7405, which is this British national grid with projection. But the raster file itself was in standard UTC, long coordinates, is that what it's called? Geographic coordinates, right, okay. So you need to warp the raster file, and in the tradition of Star Wars, there is this amazing command line warp tool which will warp your raster file to the correct coordinates. Took a bit of fiddling about, but it worked eventually. That's what it looks like when it is warped. And then finally, you get, if you run this sample function, you get an output which is effectively another column on the urban mind data, which is the value of the NDVA at the sampled locations. And then we just did a very, very simple Pearson R correlation between 2 types of data, total mental state and mental state diff, which is basically you take off you look at a participant's average, and then you look at how much their mental state differs from their own average. And the reason that you do that is that my happy is not the same as your happy, effectively. So it accounts for the fact that we have different versions of what what happiness or non-happiness is, different emotional states. And there was not anything exciting, I would say, for total mental state, but for the mental state difference score, which is in actual fact a more accurate score, there is a small but statistically significant correlation between the change in mental state and the greenness of the area. Now, it looks like a tiny correlation, but if you're doing anything in mental health, 0.13 is a good result. And a p-value of something times 10 to the minus 5 is also very good. So lots more to do because this is a small data set. But yeah, it's the beginnings of something really exciting, I think. Thanks to the team as well. Thank you. Thank you.
Well, we've run out of time. Thank you so much. If you have any questions for this group, we invite you to ask them after we close the session here. I'm just absolutely blown away by what I've seen today. This is incredible work. Thank you, all of you. Let's just congratulate each other for these projects and for everything we accomplished this week. This is really